Welcome to the first problem in our lesson 6-3 practice set. By how much does the gravitational potential energy of a 54 kilogram pole vaulter change if her center of mass rises about 4 meters during the jump? So basically, how much gravitational potential energy do we have when we're 4 meters off the ground? Pretty simple if we remember that gravitational potential energy is just equal to mgh. That's mass times acceleration due to gravity times height. So then if the mass of the pole vaulter is 54 kg, then we're going to go ahead and multiply that by the acceleration due to gravity, which in this case we'll use 9.8 meters per second squared. And we'll multiply that by the height, 4.0 meters. All right, if we have our calculator handy, then we're going to go ahead and just plug that in. 54 times 9.8 times 4 should give you something like 2116.8. That's 2116.8. But we only have two significant figures in our factors, so we're going to use two significant figures in our answer. So we're going to write 2100 joules. Good luck on the next one. A spring has a spring constant of K, which is 88 newtons per meter. How much must this spring be compressed to store 45 joules of potential energy? All right, so recall that potential energy has different formulas for different types of potential energy. So this is not the same as gravitational potential energy. In this case, we're going to have to recall potential energy when dealing with a spring, which we'll say PE for a spring, and we'll do sub EL for elastic, which is equal to 1/2 kx squared. Now, K is going to be that spring constant, which should be given to you. Well, in this case, it is given to you. And then X is going to be how much the spring is compressed. And based off of how much it is compressed, it'll tell us how much potential energy we have. That said, let's go ahead and plug in our spring constant K. That's going to be 1/2 K, sorry, not K, but 88.0 newtons per meter times x squared, and we want to know what x has to be in order for PE, potential energy, to be equal to 45.0 joules. All right, so this is going to be a little bit of an algebra exercise. I'm going to start off by multiplying 88 by 1/2, which just gives me 44. So I'm going to be looking at 45.0 joules is equal to 44.0 newtons per meter, which is just the units of our spring constant, and then times x squared. So then my next step is going to be to divide both sides by 44 newtons per meter. So if I do 45 divided by 44, that's going to give me 1.023 or so, 1.023, and that's a few extra significant figures than is required here, but we're still calculating, so I'm going to leave it like that. And what I should be left with after joules divided by newtons per meter is meters squared. All right, so I'm going to set that equal to x squared, which makes sense because x is going to be a measure of distance, and we're squaring it right now, so the meters on the left side do look right. All right, and then from here, I'm going to go ahead and take the square root of both sides because I want to know what x is, not what x squared is. So in my calculator, I'm going to go ahead and square root, and it looks like I have about 1.01 meters is equal to x. So in other words, we're going to have to compress a spring 1.01 meters if the spring constant is 88 in order to have a potential energy of 45 joules. All right, guys, good luck in the next one. If it requires 6 joules of work to stretch a particular spring by 2 centimeters, how much work will be required to stretch it an additional 4 centimeters? All right, so key word here, guys, it's saying an additional 4 centimeters. So it's saying how much work would it actually take to stretch it 6 centimeters? Because at first we stretched it 2 centimeters. It wants to know an additional 4. So that's a total of 6. So what we're going to have to do here is we're going to have to find how much work it's going to take to stretch it 6 centimeters. And then we're going to subtract how much work it took to stretch it 2 centimeters. And that will be the value we need for how much more work it'll take to take it 4 more centimeters from the 2 centimeters. All right. So what I'm saying is that the work here, or the work is actually going to be equal to the difference in our two potential energies. All right. So we know our first potential energy, the potential energy in which we have 2 centimeters, that's going to be 6.0 joules. But we need to find our second potential energy. Okay, our second potential energy is going to be with a distance of 6 centimeters. All right, so then that's going to be equal to, of course, this is in a spring, so we're going to use 1/2 K x squared, but instead of x, we're actually going to use 6.0 centimeters squared. Now, before we can actually find this, we need to come back to our first potential energy and figure out what K is. So that being said, we know that in our first potential energy, we have, of course, the 6.0 joules, and that's going to be equal to 1/2 K, and then the distance that it was stretched was 2.0 centimeters, and then we're going to square that. So now we just have to solve for K in this equation to the left. I'm going to multiply both sides by 2, so I have K times 2.0 centimeters squared is equal to 12.0 joules. All right. From there, I'm going to go ahead and square my 2 centimeters. That's going to give me 4 centimeters squared, and I'm going to divide both sides by 4 centimeters squared. So that means my K is going to be equal to, 12.0 joules, all right? 12.0 joules over 4.0 centimeters squared, all right? Now, that means that K is only 3 joules per centimeter squared. All right. So don't freak out with these units yet. That's okay. Let's just make sure we hold on to them so we don't lose track of them. Then I'm going to go ahead and plug that K into my K over here because it's still the same spring. So we still have the same spring constant. All right. So I'm going to say this is all equal to 1/2 times 3. That was an ugly 3. 3 joules per centimeter squared times 6.0 centimeters squared. And I think you'll see now why I wasn't too worried about having centimeters instead of meters in this problem. This potential energy, if I go ahead and start multiplying, I'm actually going to go ahead and square the 6. That's going to be 1/2 times 3 joules per centimeter squared times 36 centimeters squared. All right, so now my centimeter units are going to cancel. And I'm going to go ahead and then just multiply all this together, and I'm going to be left with only joules. So that's going to be 36 times 3 divided by 2. So that's going to leave me with 54 joules for my potential energy 2. Now remember what I said up here. I said that the work done to stretch it an additional 4 centimeters from the 2 centimeter point is going to be the difference between my two potential energies. So now my two potential energies are 54 joules and 6 joules. So if I set that up really quickly, the work is just equal to 54 joules minus 6 joules, and that's going to be equal to 48 joules of work required to, if we were already at 2 centimeters, to stretch it another 4 centimeters. All right, guys. Good luck. I'll see you on the next one. For our fourth problem, a 66.5 kilogram hiker starts at an elevation of 1,270 meters and climbs to the top of a peak 2,660 meters high. First part is, what's the hiker's change of potential? All right, let's just tackle that first. So we're talking about height from the ground, so we're talking about gravitational potential energy here. All right, so then we know that gravitational potential energy is equal to mgh. And we just need to think about, do we have everything we need? Well, we have the hiker's mass, so that's good for m. We always know what g is. As long as we're on Earth, it's going to be 9.8 meters per second squared. And then we're given 2 different heights, and it wants to know the change in our potential energy. All right, so then we're going to find the larger potential energy and subtract it from the smaller potential energy in this case. Well, that's just because our second potential energy happens to be the larger one. So then what we're really looking for is our change in potential energy. All right, and that's going to be equal to mgh2 minus mgh1. All right, from here we can just start plugging stuff in. Okay, we know that m and g are going to be the same for both of them, so I'm actually going to take those out and do a little bit of algebra really quickly. So that's going to look like mg, and then it's just going to be times h2 minus h1, and that's just so I don't have to do as many calculations. All right, so then I'm going to do mg, so that's 66.5 times 9.8. All right, 66.5 times 9.8, and let me actually write that down, 66.5 kg times 9.8 meters per second squared, and I'm going to be multiplying that by 2660 meters minus 1270 meters. All right, if we plug this into the calculator really quick, for my mass times gravity, I get 651.7. Then I'm going to go ahead and multiply that by 2660 minus 1270. And it looks like I get something, not worrying about significant figures, I get something that looks like this, 905863. And it looks like at best I can use 2 significant figures. So then we're just going to go ahead and call this 910,000. Yeah, we'll call this 910,000. And we'll say that this is joules. So this is our change in potential energy. Now let's look at part 2. Part 2 says, what is the minimum work required of the hiker? Oh, that's great, because we already know that the minimum work required is equal to our change in potential energy between these two. That is the minimum work required. Okay, so then we're going to say for part B, then our answer is actually just the same. And then for part C, it says, can the actual work that was done be greater than this? Okay, well, the big fat yes on there, because in reality, we never really get the full minimum work done because there's all kinds of dissipative forces in nature, like air resistance, or maybe they just didn't go in a straight line, right? Okay, so the minimum work required is, of course, the change in potential energy, but in reality, you waste a lot of energy and you waste a lot of work on just overcoming different dissipative forces. All right, guys, that's it for this practice set. I'll see you guys in the next lesson.